His career began with designing and constructing packaging for the food industry, including thin-walled containers and closures made by injection molding. He continued focusing on packaging development at Kraus Maffei, Villacron, Hitsumi, and now Baule. In the 1990s, he participated in experiments with granular components to make plates and cutlery for the Federal Garden exhibition in Germany. From 2010, the industry increasingly explored biopolymers from natural materials. Collaborating with Mr. Putsch at the Kraus Maffei Demonstration Center in Schkopau, established a nucleus for biopolymer development. The combination of a material expert and a mechanical engineer was unique for advancing biopolymer processing. Please join me in welcoming Timo Günzel, graduate engineer from Baule Intelligent Machinery, with his presentation on the topic Biopolymer Injection Molding Technology. Welcome. Hello.
Hello. I want to talk about economic processing of biopolymers in the injection molding process and the challenge of the machine maker in the future for biopolymers. When we see the market at the moment, we have a hype in biopolymers. When we see it from the machine maker side, we discuss with customers from the US over Europe to China about biopolymer parts up and down. We discuss about which materials we have to use in the future, from PLA to PBS to PHA. And when we see in the end what parts come really in the market, then we see that is very less at the moment. And we discuss internally what we can do also from the machine making side. And when we analyze the situation at the moment, is very simple. That's the parts cost. When you see 60% of the parts cost are material costs, 20% round machine costs, investment in the machine, and so on, then we have mold costs, we have manpower costs, and we have energy costs. So material cost, we as a machine maker can say very simple, Peter, that is your job to reduce it. But our job is to reduce the parts or the cost in the machining and in the engineering, in the energy consumption. And when we then make a trip to the injection molding machine, then we see some potentials, what we can use or what we can use in the future. So that is a simple injection molding machine. You have on the left side, you have a clamping unit. On the right side, you see the hopper for the material and the injection unit. And when we then go more inside, then you see on the right side the clamping unit. This is a very simple unit. You open and close the mold and eject the part out from the mold. And on the left side, you see the important system for the injection molding machine is melting the material and injected the material in the mold. When we then go deeper in the injection unit, then you see we have two systems. One is a melting system and one is a driving system for the screw and rotating, injection and rotating of the screw. That is more deeper in the screw area. You see we have a barrel, we have heater bands, we have a hopper, we have a nozzle, a check valve, and so on. So that is the typical system in this market. And when we then say, look to the market, all these things are created by plastic. That means the calculation of a barrel head, of the screws is driven by plastic. That means a normal plastic machine maker delivers machines in the market for temperature up to 400 degrees. And the normal pressure what we deliver is between 2,000 and 2,500 bar. Based on 2,500 bar and the temperature of 400 degrees, we calculate the wall thickness of the barrel, we calculate the screw head, we calculate the screws, and all these things. And when we now discuss about biopolymer, we discuss at the moment about 200 degrees. That means we can maybe reduce the steel or the wall thickness of the barrel. We can reduce the size of the screws. We can also reduce the metal of the barrel head, and that is in the end a reduction of the costs and also reduction of the CO2 footprint. You know, when I need less steel, then I reduce also the CO2 footprint worldwide. That is the situation what we have between the existing machine at the moment in the market and maybe what we have to do in the future. Then we see also the design of the screw. What we see in the market is a standard screw. You have 3 zones. You have a feeding zone, you have a compression zone, and we have a metering zone. That is so the standard design, what you find on the plastic injection molding machines. It's also designed by plastic, not by biopolymers. And when we see then here, the material comes in the hopper on the right side. In the screw, we rotate the screw, feeding the material in the front of the screw, and in the middle we have a compression area. Here we create, with the design of the screw, a lot of friction on the plastic material. What I have learned from you, Peter, is friction is not good for biopolymer, really not. So, and that we have also to learn as a machine maker, that we have create new designs for the screws. That means maybe is it so a design that we have more a feeding area and have maybe between the check valve or the end of the screw, we have then a very small compression zone, and we have a very small metering zone. That means we have to work on the designs of the screws. And also we have to work on the steel base on the screws. I had a discussion with some guy here yesterday here to the maximum residence time of the material in a barrel under temperature. And he say, hey, it comes maybe water out, or it comes some acid out, and the normal steel what we use in the plastic industry at the moment is a simple steel, a mold steel. So, and here we have also to think about what we can do in the future, maybe surface coating or whatever. That makes no sense when we deliver machines in the market and the customer use biopolymer, and after a half year comes the customer back to us and say, hey, I have a lot of corrosion on the screw, and the screw cost is, a small one is maybe so 2,000 euros, and the big one is then 20,000 euros. So then we have a huge discussion. And here we have also, from the machine maker side, to look what we do and what we have to do. The next point is a drive. We have 2 drive areas. We have one is the rotating of the screw to feeding the material in the front of the screw, and one drive we have to inject it, the material in the mold. Here we have the situation that we have to rotate the screw very slowly for biopolymer to bring not a lot of friction inside. When you see on the technical part, or on the biopolymer, we have to rotate maybe maximum 350 millimeter per second. On the technical parts in plastic, you can do it with 700 millimeter per second. And the packaging parts, or the packaging guys, rotate the screw with 1,200 millimeter per second. That means for the biopolymer machine, I need a drive with very low rotate speed. That means maybe I can reduce this drive. When we analyze the torque of the biopolymer in the screw and the speed, then we can reduce in the end the drive from the power and from the performance. That is also cost reduction, very simple cost reduction. So, but we need also alternatives. We discuss a lot of things in packaging. And when we see packaging, a normal yogurt cup runs in 3 seconds at the moment with 4 or 8 cavities. And these guys have a lot of throughput of material over the screw. And here we need, for biopolymer, alternative solution. That means maybe we go the way that we optimize our screw design, or we go the way that we make a pre-melting unit, you see it on the top, and bring it in a injection screw inside. And here we can realize a lot of throughput also on biopolymer with less friction, with very perfect holds the temperature, and that can be an alternative, special for the packaging industry. In the technical parts, I see not so the biggest throughput, but in the packaging we have to discuss, or we have to develop systems in the market, or for the market. So our homework for the future is, we have really to analyze, and that we want to do anyway with Peter together, what is really the injection speed, what we need on the machine, what injection pressure we need on the machine. Based on this result, we can overwork the main power of the machine and can maybe reduce some things on the machine. That starts with the drive, and it starts in the end with the mechanical properties of injection unit. That is one point. Homework is also, we have to analyze what is really the inner pressure when we injected biopolymer in the mold. Based on that, when we see here differences, maybe we can make the wall thickness of the platen smaller, or we bring maybe systems in the market that we have maybe a 50-ton machine, which have at the moment maybe a distance between the tie bars of 400 millimeter. We bring a 50-ton machine with a tie bar distance of 1 meter in the market to produce really, from the cost side, biopolymer parts on a better way. And next step is, when we find out that we can reduce the inner pressure in the mold, of course, the mold maker have also do your job and say, hey, maybe I don't need so a stable mold for these parts, and you know, steel costs money. And in the end, we can also reduce the cost of the molds for biopolymer parts. Here we have simple calculate what we mean, what we can do. And when we see all these facts at the moment in the market and make our homework, we can maybe reduce the cost of the injection molding machine between 25 to 30%. So that means, in fact, that is a lot of money. You see that here. That the invest of a biopolymer machine goes down, and then you can produce parts with lower costs. So also, the discussion about the energy consumption. When you see most of the machines which we have in the market at the moment have energy consumption between 0.3 and 0.35 kW per kilograms. I can say a number. At the moment, we have worldwide installed around 1.2 million injection molding machines. So that is a lot of energy what we need for this machine. The modern machine have at the moment, also when you buy now a machine, a standard machine, you have between 0.2 and 0.25. Okay, you reduce it one by one. But you see, when you calculate it based on the biopolymer, then we can reach a level of 0.12 to 0.14, and that is a huge impact. When you bring biopolymer in the market, you bring the right machine in the market, then you can reduce worldwide the energy consumption for produced parts. That is the calculation for the customer. That save also cost for the customer. And that is the slide what I show on the start. we can reduce the cost of the machine. We can reduce also the energy consumption when we build an injection molding machine special for biopolymers. And my summary is very simple. The biopolymers have a huge impact of the industry, but I'm sure that also the biopolymers will have a huge impact of the manufacture of machines. That means we reduce the cost, we reduce the parts and the steel of the machine, and that save CO2 footprint. That is what we see from a Bohle side. And where is Bohle? Bohle is an innovation company from China. We have a production plant in China, too. We have a production plant in India. We have our headquarters in Europe is in Poland. We have also a company in the US. And we can say now we start also with the Bohle Intelligence company in Merseburg in Germany for make R&D in Germany. This gives you 2 points. One, I mean, we have a right place here to make R&D in the area Merseburg. And the second point is very simple. In China is nothing confidential. When you make in China developments, then you can make it on a central place in Melbourne, and you have and all guys knows it. And that's also the 2 reasons that we go really to Germany and to Merseburg and start to make some developments, and special around biopolymer.
Yeah, thank you, Timo. Great experience you brought with us, and great calculations so far. I think that's something that really brings benefit also, and some more numbers to the audience. Any questions from your side here in the room?
Yeah, Timo, what do we do with the energy regain for using the chiller, or the fact that we have to cool down the mold? Can we reuse this energy somehow in the process? Also for biopolymers, of course.
That is difficult. That is difficult. Normally, is it so? You come when you see biopolymer against plastic, you come anyway with lower energy in the mold at the moment. I mean, the cooling down effect is not so important anymore. And you can also reduce the chillers, or the sizes of the chillers. At the moment, you have maybe on the normal machine 16 kW chiller. Maybe you can use it with a biopolymer, maybe with a 9 kW chiller. And also, these systems have right now also servo pumps inside, and these systems really start cooling when you need cooling. And I'm sure that's the reservoir what we have on energy. We bring it back maybe to the screw or whatever is so small that make no sense.
Could we use it for a dryer to dry the material, maybe?
Maybe, but we produce injection molding machine.
Okay.
I'm not a dryer expert.
Okay.
Maybe that can be a problem.
Thank you.
Yes, please.
I have a question about the, let's say, future of machinery, because in the first part we have heard few speeches about bioplastics, and they are changing the industry quite significantly. And actually, as I don't understand, for example, with Alec from New Zealand, he was talking that they are going to develop a new industry for these materials. But from your side, you are like building the conventional industry, injection molding industry, but which is tuned to the new materials. Do you see any like perspective or potential for the company to develop a new methods for processing, maybe some modification of injection molding or some completely new methods for working to work with bioplastics in principle?
Yeah, when we see the discussion here, of course, the first step for us is to to look what is the future market. And we prepare our machines of the future market. That means when the biopolymer market comes more and more, then we have to bring a biopolymer machine in the market. But of course, when we had a discussion from here yesterday, that maybe biopolymer is from the cost higher, sometimes from the weight are more heavy. So, and here we have also to look in other applications. So that we really look, is standard injection molding for some parts the right process? Maybe we make combination process, maybe injection molding with blow molding or thermoforming or whatever to bring other parts on the market. But here we have to make our homework. That means we have exactly to look what is really the stability of the material. When you make, for example, you make a cup at the moment, polypropylene cup for yogurt have a wall thickness of 0.35 millimeter. Mm-hmm. Maybe we can do it with a biopolymer in 0.3, but then we have to check is this cup really stable for the transport and so on. And maybe we can also think about that we implement a new process to reach the 0.3 millimeter on the cup. And here we have to think about.
So for your company, let's say so, it is much more efficient to follow the market rather than to jump in front of it. Like
we won't jump in front of that. Very simple. That is the reason that we implement an R&D center here. So we want to push the industry with new solutions, with new ideas. But that is also the reason that we implement that it is a little bit confidential. What we want to.
Okay.
This is
Thank you so much. Thank you.
Yeah, but listening to the discussion, Peter, looking now in your direction more or less, maybe we also need to go one step in between those parts and the machinery, and also invite someone of the hot runner and guys and also listen to them. And but we have another guy with a question, please.
Yes, thank you. So maybe just to follow up actually on that theme, I think one opportunity that comes with biopolymer, in talking about new processes, maybe a new aspect is biocomposites, because I think previously with polyolefins, it didn't make that much sense to have biocomposites, right? You have PP or PE, which is recyclable. You add a fiber, then your material is no longer recyclable because you've contaminated it. And it's also non-degradable because the matrix is non-degradable. I think with biopolymer, it brings biocomposites sort of back on the table. It has opportunities now that we have a matrix that's biodegradable. And so with that in mind, are you also preparing machines for biocomposites, which also requires some modifications with the presence of fiber, the high thermomechanical shear?
We built injection molding compounding systems. That means you can, on this machine, you have a pre-melting screw. You can put, you melted the material and can put additives inside and also natural fiber inside and so on, and can build your compound, bring it in the injection screw and inject it that we have right now in the program, but it's also driven by the plastics. That means the guys make compounding based on glass fiber, carbon fiber and so on. But this technology you can also use to make composites in the biopolymer industry. But here we have the same discussion. It's also created by plastic. Here we have also to say we have the right screw, we have the right heater elements. Do we need so a big barrel? Maybe a small barrel is better for biopolymer to reduce the cost of so a machine. And when you then inject it and have an inner pressure of 500 bar, then you have to calculate the clamping force based on that. When we see biopolymer, we have maybe 350 bar, then we have a half of them. That means the cost of the injection system is maybe 30% less. So that we have to calculate.
Yeah, thank you for the really good questions.